So we are very familiar with the Cartesian plane. We've been doing that since middle school. But now we want to add some depth, right? And so when we look at word problems, we're going to look at how they're traveling to the horizon, as well as what's going on with like a wind effect on it and things like that. So 3-dimension is really just adding another coordinate. You do everything exactly the same, all right? So we are going to attempt to graph these, which is why I have graph paper for you. And so that first one is plotting a point. You'll notice that your X and Y are that little 2-dimension flat piece down there. And then you'll see that the Z goes straight up. When we're looking at this, a couple things, personally for me, I would probably write a positive and a negative on this thing. Okay. All right, I personally would. Because if not, you're going to get confused. So if I am looking at the XY right here, I would say this is positive Y. Think of it as going up. Like if you were to flatten this up on the screen, this would be negative Y. If that's the case, then this would be positive X and this would be negative X, right? And Z's fairly obvious, right? Z's the easiest one to see here, positive and negative. And so one way to graph these, I always start with my X and Y because that's what I'm most familiar with. It's also the easiest piece to graph, okay? You'll notice in the book that they do like a 3-dimensional box. So if you've ever drawn a 3-dimensional box and you just draw those parallel lines to make it look 3-dimensional, that's a good way to draw it. And so if I am graphing this, I'm going to go to the positive 3 on the X, just like I would my X movement first. And then I would go to the positive 4 on the Y, all right? So positive 3, positive 4, and that's going to plot it like this. So if I were to draw these little dashed lines, positive 3, and then up to positive 4, you see you're right here, okay? Now on the Z, I am going up to 5. So if I go all the way up to 5, which is up here, then I would, if I were to box this out, I would say, well, I moved positive 3, and I moved then positive 4, and it's going to drop me up here somewhere, up 5. All right, so you can't think of it way up here. Well, let me draw my little lines a little bit better. I might go out. So if I go up here, all the way up to 5, it's somewhere in space. So I went 3x, 4y, and from this point I went to z. And so this is where my xyz point would be. So it looks like it's a lot closer, right? But we went straight up from this point here. So we found this point on the 2 planes first, and then we just went straight up to the 5 from there. If I went up to 5, did I go all the way up? I did go all the way up. There we go. There's 5.
Oh, okay. I was so confused. I was like, hold on.
There we go. All right, and then we're just going to label it. Or if they gave us a point like they did here, you could label it with the point itself. All right. You do not have to draw the box. All right. You do not have to draw the box.
Okay, that's what I was waiting for.
Right. Now, I do want to see your movement here. Okay. Not so thick, but I do want to see that movement. But you don't have to draw the box when you graph these. You just want to give a visual of where it is. If I were to draw a vector, it would go from the origin. It would go from the origin. So if I were to draw a vector on this, it would go from here, and it would go up to that point there. All right? If I were to draw a vector.
Not yet.
really be easy compared to what we've done for sketching.
Yes.
Distance and midpoint is literally the same exact formula. You're just throwing in an extra coordinates, right? So if I want to find the distance of this guy, I am going to take the square root of my x's subtracted plus my y's subtracted. Watch your positives and negatives for all my positive and negative fans. And my z's subtracted and squared. All right, so identical. You just have a third coordinate there. And I'm not going to make you do it in radical form. That's fine. I'm not testing your ability to do radical form. So if you round to 1 decimal place, that's fine. If you were to give me an exact, you would need to do your radical simplification. Midpoint is also identical, except you have a third one. So you're going to add your x's, divide by 2. Add your y's and divide by 2. And then add your x's and divide by 2. And it isn't, for a midpoint, it is an XYZ coordinate here. So you do need to list it in parentheses with your x, your y, and your z. So it's going to look like this. But again, it's the same process. All right. It could list it like this, or you could, it would be the same question, but it would look like this. So these two are the same answer. Let's talk about component form and direction. We are going to use direction with degrees as well, but we're actually going to do them separately and do that. But in this case, it wants component form, and then it wants its length. Once you have component form, you've already subtracted your x's and your y's and your z's. So you can go straight to just squaring those, because once you have it in component form, you've done that first piece of the distance formula. And then a unit vector in the direction of this. Unit vector, remember, was something we did also at the beginning. We did the vector over the magnitude. That's unit vector, which makes sense. All right. A unit is when you divide by, get it into unit form, like miles per hour is a unit form for speed. All right. So the two things that we're doing here really are doing what we've done before. Component form, you're going to subtract your ending minus your beginning. Okay, so the point where it ends, subtract the point where it begins. To find your length or your magnitude, you're just adding a third piece of that. The x squared, the y squared, and the z squared. All right, it's just like your distance formula like you just did. And then unit vector, you're going to take the original vector and divide each piece by that magnitude that you found. And that would be your unit vector. All right, so if I were to take these and I want it in component form, this is remember, A is your starting, B is your ending. Initial and terminal point are important. We're ending at B, so we're going to subtract this direction. 3 minus 5 is going to be my x. 6 minus 1 is going to be my y. 2 minus a negative 1 is going to be my z. And that's going to be this guy in component form. All right, so I'm going to end up with -2, 5, and 3. That is this vector in component form. All right. If I want to find my length, well, once I have it in component form, I've already subtracted the piece of it that I need to, so I can just go ahead and square it. So the length then, when it's asking for that piece, then I am going to say the length is just going to be the square root of the -2 squared plus the 5 squared plus the 3 squared. All right, that will be my length, approximately 6.2 here. All right. And then a unit vector. A unit vector is going to take, and this, by the way, was square root of 38 before I did that, because you're going to want to use the square root of 38 when you do the unit. So when you do unit, do the exact, don't do the rounded. You don't want a fraction with a decimal. So the unit vector is just going to take each piece of this and divide it by that. So we're going to say the unit vector is going to be -2 over the square root of 38, 5 over the square root of 38, and 3 over the square root of 38. That's not in simplest form, right? I don't want a radical in the denominator. So I need to multiply top and bottom by this square root of 38 for all of these, right? And then simplify if you can. So you end up with -2 square root of 38 over 38 5 square root of 38 over 38, and 3 square root of 38 over 38. You can reduce this guy right here. All right. This is identical to what we did when we had an XY, two-dimensional. You can add, subtract, multiply, etc. with vectors. So if they give you these three vectors and they want you to do something like 2p plus q, you're literally just going to do your distribution, that's your scalar, and then do your addition. All right. So it works the same. I don't know that we need to spend a lot of time on it. Pay attention to your positives and negatives. Pay attention to your distribution. I will say if you have something like this, -3, I noticed this when I was checking y'all's work. When you have something like a -3 there, you're either distributing a 3 and subtracting, or you are just distributing a -3 and adding. Don't do both, okay? So by that I mean, if you have something like this for my guys with positives and negatives, if you want to do this, then you distribute a negative through, okay? But don't leave it a minus and distribute a negative. You've done it twice at that point, okay? So just be careful of that when you are subtracting these. And that's true of anything that you're subtracting with a distribution. Dot product is also the same when we are doing, finding like the measurement of what's going on in between. Remember dot product, you would multiply your elements and then add the products. Well, now you just have 3 of them. Multiply your x's, multiply your y's, multiply your z's, add those up. That's your dot product. So if I were wanting to find the angle here that I'm looking for, I can still use my cosine of my dot product over my magnitudes, all right? I just have to think that I have 3 of them. So I just have 3 elements within the vector. I have 3 dimensions within the vector, but everything else works the same. So if you look at this, find the measure between the angles. If I want to find that dot product, I'm going to just do my product and my sum between those 3. So this is going to be exactly the same. I'm going to say, well, the cosine of theta should equal the dot product of these, which is going to be -5 times 1 plus 2 times -3 plus 0 times -2. That's my product over the magnitude of each of these. Well, the magnitude I've already figured out is going to be just my square of the 3. So this magnitude, and it is times, not plus or minus down here, the magnitude of this second one. It's plus within it, but it is multiplying when you do the 2 magnitudes together. All right. So you can calculate these. You can multiply within the parentheses as well. In your calculator, just to make sure you're doing these correctly, you can do your cosine in your calculator. 11 divided by, the square root is going to open a parentheses. You can say 29 times 14 in those parentheses. All right. And you will get your rounded to the nearest degree would look like that. All right. So It says an airplane taking off at a heading of 180 degrees has an air velocity vector directed 20 degrees above the horizontal and an airspeed of 225 knots. There's a 40-knot wind from the southwest. Find a vector that represents the plane's velocity relative to the point of takeoff. You can draw two-dimensional, okay? Because really what they've done here for you is they have set 180 degrees. Well, 180 degrees has no x movement whatsoever, okay? No x movement whatsoever. And so when you think about these, you are going to think about the fact that your vector now has 3 dimensions, okay? So when I do this first one, I'm going to deal with just the airplane first, and then I'm going to deal with the wind, okay? The airplane itself, that vector is automatically going to have no x movement. So I'm going to put a 0 in my x value for that plane's movement there, okay? We have no x movement if I'm going 180 degrees. Does everybody see that? No x movement, all right? If I am going 180 degrees, remember, this is the negative, so it's going to look like that for 180. And then it's 20 degrees above the horizontal, so my z, that's beautiful, my z is going to be right here at 20 degrees, all right? 20 degrees. And how fast am I going? Well, I'm going 225 knots. This is why I'm going to use cosine and sine here, all right? Because based on this, if I were to look at this, my left and right movement compared to where the plane is going to be my middle one here. And my up and down movement is going to be that last dimension there. Okay, so we're talking about a bearing, not a standard position. A bearing, not a standard position. No x and y movement if you're going straight down. It was as if they could say he was going due south. That would be the same thing, okay? In an XYZ, all right? So this is the airplane. So this is my vector for my airplane. And then we're going to talk about my vector for my wind. All right, so for my wind, when I do my wind, it's not going to tell you that the wind is going up or down. So it's not going to give you a third dimension for wind, okay? Wind is below, they're not, at this point, they're just going to tell you if it's blowing X and Y. So when I do my wind, I actually ignore my Z, and I'm just going to picture what it would look like on an XY. So I'm going to draw this little XY that I've always known, okay, to do my wind. Because it's not telling me the wind is blowing left and right and up and down, okay? It's not going to give me 3 dimensions for my wind, all right? And so it says 40 knots from the southwest. Where is southwest? Well, southwest is down here. Everybody agree this is southwest? But it's from the southwest. So in standard position, it's going to be right here, yes? All right, and if it tells you a direct southwest, you can assume it's a 45, okay? If it told you a different one, it would give you a degree measure. But from the southwest, you're going to assume it's a perfect from the southwest, which means it's going to be a 45. All right. In this case, I do have x movement, 40 times the cosine of 45. I do have y movement, 40 times the sine of 45. I do not have z movement. Okay. I do not have up and down movement. This is just telling me my wind blowing this way. So that's why I drew it on a separate XY plane. I don't even want to consider a Z, all right? When I add these, then I'm going to add the 0 to this guy. I'm going to add the Y's, and I'm going to add the Z's to get my new vector, okay? And so that you're just plugging it in and rounding to the nearest, which we all know how to do. All right? That is my where he is 3-dimensional. That's where he would be 3-dimensional, okay? We have our X, our Y, and our Z.